I hope you are able to follow up with what we were discussing in the last class. So I could not recap because of the, the time constraints that we have. But anyway, we will make this things clear so that we will do that. So I don't want you to get confused because there's going to be one RSA algorithm as such has, several steps that we are going to use, and each one follows certain algorithm. Okay, so that is something which we have to understand. So if you look at the notepad file that I'm saying, so we are ultimately going to generate the public and private keys. This is what our goal is. Okay, so if Alice wants to talk to Bob, what should Alice use? Can anyone tell me? Alice wants to use asymmetric
Sir,
key cryptography.
are
Yeah.
you sharing screen?
Oh, I'm sorry. Okay. It got disconnected. Okay. Is it fine now?
Yes, sir.
Okay, okay. Thanks for pointing that. Okay, so I was just thinking that you are all seeing the screen. Anyway, sorry for this. Okay, so asymmetric key cryptography. We will look. We are going to focus on the RSA algorithm. As you remember, RSA it stands for the three guys who came up with this algorithm: Rivers, Shamir, and Edelman. Okay, so those first three letters, the first letter of each guy's names is what RSA is, right? And RSA is an asymmetric key algorithm. As you know, it has a pair of keys. So the private and the public key, which means if Alice wants to encrypt and send a message to Bob, what should Alice do with the plain text? Can anyone tell me? Can you recall that? 13 have joined. Did you remember the logic that I told you in asymmetric key cryptography? If Alice wants to talk to Bob, send a message to Bob, right? What should Alice do? Alice should do the encryption algorithm, correct? And so when he wants to encrypt the plain text that he has, right, he needs the key. What key he will use? Can anyone tell me?
Bob's public key.
Bob's public key. Very good. So the Bob's public key is something which is known to the world, known to the it's globally known. Okay, so he has to use Bob's public key and encrypt and send the cipher. Now this cipher, if someone tries to basically hack or try to break the cipher, they need to know the private key of Bob, right? This is what is very difficult to find because only the public key is known to the globe and not the private key. Okay, so that is the concept that I was trying to tell you. So how are we going to generate this public key and private key such a way these are pairs, right? Say for example, I'm going to use multiplication on one end. Bob is going to do the reverse of it. He's going to do the division. Here we call it as a multiplicative inverse of it, right? So the public key is going to be used at the encryption side and the private key is going to be used. So this pair of keys, how we are going to generate, the base is we are going to start from dealing with prime numbers. Okay, so that is the first point. But as such, we can't just take away to random numbers and then form these keys. So we are going to deal with a lot of max here. So I'm going to deal with prime numbers. I'm going to teach you what is Euler's Docian function. Right, this is going to be a function which we're going to use to generate our pair of keys. Okay, so ultimately, these keys that we're going to generate are going to be treated as exponents. So we're going to deal with exponentiation, right? Any base a power x that you have 2 power x, that x exponent, right? And that is the way that we're going to use the keys. The keys are going to be used as exponents, right? So we're going to deal with exponentiation when we do encryption. So the exponentiation that we're going to deal again is going to be in terms of modular arithmetic. So we're all doing modular arithmetic in cryptography. So we're going to use something called as modular exponentiation. See, I'm telling all these because I want you to take these new topics into your mind because I'm going to teach you separately on modular exponentiation where we are suppose you have 2 power 10, right? 2 power 10 is, you have this exponent value 10. So which means traditional multiplication will be multiplying 2 10 times, right? So that is something which we are not going to use when we are doing this bitwise calculations. We're going to use an algorithm which is going to be fast enough and not exponential time complexity. We are going to do something where it's a procedure called fast exponentiation. So instead of doing a traditional multiplication for doing the encryption or the decryption, we are going to do something called as a fast exponentiation, which is a square and multiply method. So I'm going to teach you that. Okay, so encryption and decryption, we're going to do modular exponentiation, but the keys that we're going to generate, right? We're going to deal with prime numbers, and we're going to get two pair of keys, and one is going to be public key and other is going to be private key. Those public and private key are going to be treated as exponents, right? So that is something which we are going to use to basically encrypt and decrypt, right? So if I get a public key, I have to get the inverse of that so that I could do use that as a private key. So I'm going to do say multiplication there. I'm going to do division at the other side, which is going to be the inverse of this value. So that we will deal, such a way that they are co-prime and all that. Okay, so this pair that we're going to deal, we have to find out what is the private key given the public key, this pair. For that, we have to find the inverse of that value, multiplicative inverse. So I'm going to use extended GCD algorithm. GCD algorithm is greatest common divisor. That's something, extended GCD is, I'm sorry, it's actually extended Euclid's algorithm. Have you heard of Euclid's algorithm? Anyone? I think in your base. Can you raise your hands if you heard of Euclid algorithm? If you don't know, it's easy. I'll teach you. So finding out the greatest common divisor, Euclid's is a much effective way to do that. But we will extend that Euclid's algorithm to find the pair. If public key is there, what is the corresponding private key pair, right? This is something which we will be using. Okay, so can we get started? Okay, 14 have joined. Can you raise your hands if you're all ready and you're able to at least get the topics that we're going to look at inside the RSA algorithm? Okay, so I'm getting some hands raised. Thank you for that. So let me get started. I hope you remember that I was talking about some set, right? So we're going to deal with integers. I said let's use the domain or set called Z, right? And that Z here we were not just dealing with negative or positive integers, but we are now going to play with modulus, this Zn. So what is Zn is basically set of residues, because as you know, we are doing modular arithmetic here, which means I have a integer a, I do mod n of that, which means I divide a by n and get the remainder of that, right? And the remainder is going to be a value integer between 0 to n minus 1. Right? So that is the thing here. So this is called set of residues where we are doing modular arithmetic. So always mod n comes. And so the set that you have that can comprise of the elements between 0 to n minus 1 is going to be put in Zn. Right? So this is what we have shown here. So Z13 here is going to be what? Any number that you go on to divide with modulus of 13, right? The remainder is what is going to be comprising of that set, right? And it could be from 0 to n minus 1, right? But we are going to go further. We're not just going to use set of residues, but I'm going to now very much focus on choosing integers such a way that they are going to be co-prime to each other. Co-prime are relatively prime. So these two words can be used synonymously. So we say two positive integers a and b are going to be relatively prime to each other, which means what? The greatest common divisor to divide that, right, when they both are co-prime to each other, is the GCD of that is going to be 1, right? So the greatest common divisor is only going to be 1. Only 1 can divide both the numbers, right? So that's the point here. So we're going to use a set where we are going to deal with such a way that suppose I put Zn star, right? So this is the representation to deal with such a way all the numbers that are going to be smaller than n in the set is going to be relatively prime to n. So what do you mean by that? So I need to find, so Zn is not going to be equal to Zn star. So that is the first point that we'll have to understand here. But if n is a prime number, right? Say for example, 13 is a prime. Now I need to know what are all the elements in the set, such a way all the elements in the set are going to be smaller than 13 and they're going to relatively be prime to 13. That is the point here. Right? So what will all be the elements in that set? 0 is not going to be there, right? So 1 to 12, if you look at here. So 1 and 13, if you take the GCD of that, it's 1, right? Only 1. So 2 and 13, again, the GCD is going to be 1. So you can't can't be dividing both 13 and 2, right? And 3 and 13, again, the GCD is 1. 4 and 13, GCD is 1. So which means what? If the n value here is a prime number, then the number of elements in the set, if you look at, Can anyone tell me what will be the number of elements in the set? If Z13 star I represent, where this n value is a prime number, so the elements in the set that are going to be smaller and relatively prime to 13 will be what? Will be from 1 to 12, right? So which means that you have n minus 1 elements in the set. This is the case where the n value is a prime. You get the point? So that is the first thing that we have to understand here. So generally what we're going to do is we will deal with this. We say if a number is a prime, let us use this symbol called letter called P. And if the number is a composite number, which means that it could have multiple divisors, then we will use this n so that we're not going to get confused. So I use ZP star if the P is a prime. And the number of elements in that set such a way that all are relatively prime to P will be what? 1 to P minus 1. Okay, so that is the point here. But that is not going to be the case if I choose a value n such a way that it's not prime. Say, for example, I choose Z10 star. Can you tell me what are all the elements in this set such a way that they are co-prime or relatively prime to 10? Anyone? I hope you're following what I'm trying to say. So you know that 10 is not a prime number, correct? So I want to know Z10 star, the set of these, the set that comprises such a way the elements in this set are going to be smaller than 10 and relatively prime to 10. Relatively prime to 10 meaning the GCD is basically 1. Okay, so can anyone tell me, will 1 be a part of the set?
1, 3.
1, 2. 2 will not be part because the GCD you know that it is going to be 2. 3 will come?
Yes, sir.
And 7. Then what will come? Yeah.
7.
4 will not come. 5 will not come. 6 will come. 6 will not come. 7 will come.
Yes, sir.
7 will come. Good. 8 will come. 8 will not come. 8 and 10. GCD is not 1, right? And then 9 will come.
Yes, sir.
9 will come and 10 will not come, right? So so there are only 4 elements in this set such a way that they are relatively prime to this, right? So I have given you a very small value and you're able to compute all the elements in the set. And you could say the number of elements in this set is 4. Z10 star, if I tell you the number of elements in that set is 4, such a way these are the 4 elements which are smaller than 10, right? And relatively prime to that. But if I give you a very large value and I want to find the number of elements in the set, then it becomes slightly difficult. Okay, so this is where we are going to bring in Euler's phi function. So I want you to take a notebook. We will now start to compute quickly because I'm going to use Euler's phi function extensively in order to generate the private and public keys pairs, right? And so it's very important for you guys to understand what is Euler's phi function. This is also called as Euler's torsion function, right? And it's going to be playing a major role in asymmetric key cryptography. Phi of n, that is the way that I'm going to represent. So what is phi of n? Very simple. Phi of n value will be what? In this case, that example that I was showing you, phi of n value will be 4. So it is only going to tell you the number of elements in the set such for Zn star. That is what Euler's torsion function will tell you. Okay, for that it has certain formulas, right, where you can go on to just apply and get the number of elements in the set given the n value. So can we now try to understand this? So phi of n, if I have to define Euler's torsion function, it is going to return the number of integers that are both smaller than n and relatively prime to n, which means the GCD is 1. Right? So I hope you have understood what is Euler's torsion function. So let me now give you 4 formulas or 4 rules which we can apply. We can do a combination of that also in order to find the Euler's torsion function value. So these are the 4 properties of Euler's phi. Can you note down this, all of you? I want all of you to remember this because we're going to use this in our RSA algorithm. So the first property says phi of 1 is going to be 0. What does it mean? If n value is 1, the number of elements in that set that's going to be smaller than 1 and relatively prime to 1 is going to be 0. This is the first property. Okay, please note down this. I want all of you to write down and do because otherwise you will lose the focus. The second property says if you want to find phi of p, where p is the prime. So as I told you, I'm going to deal with representing prime number by using this letter p. Okay, and composite number, let's probably use it as n for example. So if P is a prime, then you want to calculate the number of elements in that set, which means ZP star. I want to find out what is going to be the number of elements in that set. I already told you that. Can anyone tell me? If P is a prime, right? So the number of elements in the set ZP star such a way that is smaller and relatively prime to P will be what? How many elements will be there? Will be P minus 1. So note down this, right? So the second property says phi of P is equal to P minus 1. Very simple here. Say for example, you have 3 as a prime number, right? So if you want to find Z3 star, right? So the number of integers which are going to be relatively prime to 3 and smaller than 3. What is going to be the set that you have? It is going to be what? 1 and 2. So you have 2 elements in the set which are smaller than P and relatively smaller than 3 and relatively prime, which means that GCD of 1 and 3 is 1, GCD of 2 and 3 is 1, right? So that is the point here. It's very simple, right? So phi of P, where P is a prime, the number of elements in the set is going to be P minus 1. So phi of 3 is 2. Okay. So now let's get on to the third one. Now here is where you're going to now deal with a larger number and you're trying to factorize that number. Say for example, I have a product of 2 numbers, 2 integers, say m cross n, right? Now, if m and n are relatively prime to each other, m and n are relatively prime to each other, are co-prime to each other. What does mean? GCD of m and n is 1, right? Which means you can now apply Euler's torsion function separately on to m and n, right? And then do the product of these two. So that is the third property that it says. Phi of m cross n could be calculated as the number of elements in that set could be calculated separately by phi of m and phi of n and multiply these two values. You will get the number of elements in that set. So what I'm trying to say here, I am a set which is m cross n star. I want to find the number of elements such a way that it's less than or equal to m cross n. So then I could do that provided m and n are relatively prime. This is the third property. So I want you to note down this. This is very important for the RSA that we will use it. The third property is of Euler's phi. And the last property is going to be the ultimate, where if you can represent, because we are dealing with exponents and all this. So if you have a prime number P and to the power of some exponent, you can express like that, right? You want to find the number of elements in the set that is relatively prime to P power E, right? Where P is a prime, then the number of elements in the set could be calculated as P power E minus P power E minus 1, right? So this is the fourth property, right? You can combine these couple of properties in order to find what is a Euler's phi function, right, of a specific composite number or a prime number or whatever it is. So that is the beauty that we're going to do. So have you all noted this term? Last property is phi of P of E is equal to P of E minus P of E minus 1. Here, if P is prime, then you can apply this. So it does not stop here. Say, for example, you want to club the third and the fourth, you can still do. So how do you do that? Say, for example, have you noted down all these 4 properties? Can I just hear from you? Raise your hands if you have noted down. I don't want to hurry this because once you have understood this, then it will be easy for you to do. Okay, good. Thanks for that. So let me go on. So now I'm not going to just stop with these 4 properties. We'll combine these couple of properties. So third and fourth is something we will use more as a combination. So we will try to look at this. Say, for example, right, I have a number n, composite number n, and I can factor this as a product of some primes, right? That is a beauty that we are going to deal with. So n, say, can be factored as p1 e power 1 something, so p2 e power 2, so on, pk e power k. So you can express this as a factor of some primes to the raised of exponents, right? Now I know that the third property says if you have you have to multiply several numbers where these are relatively prime, you can individually calculate the phi function of that and get the product of the values. So I could now combine the third and the fourth. So if this n is going to be factored as product of these numbers, then I could individually calculate by using the property that we were trying to use. So here I could use, so I have to calculate phi of n, right? So when I have phi of like this, right, you know that I could individually calculate the phi of the individual value. So what is phi of P1 of E of n? It's going to be P1 E1 minus P1 E1 minus 1 into P2 E to the power raised E2, right, minus P2 E2 minus 1. So like that, we could go on and apply the third and the fourth property together in order to do this. So why are we all doing that is, now I will tell you a secret. Okay. We are basically going to have a very large n value. This is the modulus value that we are going to use in RSA. We are going to have a very large n value. How are we going to get this very large n value? Is going to multiply two large prime numbers and get that n value. And from that n value, we are going to find phi of n. Okay. So since I know I have obtained n by using these two prime numbers, I will be able to use phi function and calculate phi of n very easily. But the reverse of that is going to be very difficult. Given given a large n, you want to factorize and find out what is a prime. It's be very difficult. But this is where we are going to understand, how inverse function decryption is not just going to be an inverse function of this, right? And so it is very, very important to use phi function, because based on phi of n only we are going to find the private and the public key pairs. So, right, we will try to understand. So the difficulty of finding phi of n depends on the difficulty of finding the factorization of n. So I should not be able to factorize given n such a way n is very large. So we will understand this shortly. Okay, so if you're not able to understand this, don't bother, but let's get on. I'm going to now make you to apply all these rules, and I'm going to give you problems. I should have removed this, but anyway, now the first problem goes like this. I want you guys to find out what is phi of 13. Can you tell me what is phi of 13? Which rule will you apply? So the first problem goes like this.
12.
Yeah. So how did you say that it is 12? Can you justify which property did you apply?
Prime number comes in
Yeah.
second property.
Very good. So it goes with the second property. Very good. So let me now give you the next example. I want you to find what is phi of 10. The number of elements such a way that they are smaller than 10 and relatively prime to 10. Which property will you use?
Third and second, sir. Phi of 5 into phi of 2. Then 5 and 2 both are prime. So 4
Excellent.
into 1.
Excellent. Very good. Okay. So 10 could be expressed as the product of say 2 into 5. And you know that 2 and 5 are relatively prime. The GCD is 1. So now having expressed this as a product of that, I could individually compute phi of 2 and phi of 5 and apply the second property. These two are prime numbers. So this phi of 2 is going to be 1 and phi of 5 is going to be p minus 1, which is 4. So the number of elements in this set is going to be 4. You directly got the number of elements in the set. But if you have to find out sets 10 star, then you need to know 1 is going to be one of the element, 3, right, 7 and 9, right? So this is the elements in the set. But number of elements in the set is what Euler's torsion function tries to do. Right, I hope it's clear. I'm going to give you much more examples. So I want you guys to do. So can you tell me what is phi of 240? So I'm going to write this here. I'm sorry. What is phi 240? This is going to be slightly complex. Can anyone try out? Phi of 240. What is the number of elements that are smaller than 240 and relatively pi to 240? I want to know the number of elements in the set by using the Euler's torsion function. Very simple here. What I will do, I will tell you. Now you have 240, right? You try to factorize it. Don't now look at whether they are prime, relatively prime and all that. So the simplest way to do this, okay, I will look at whether I could factorize using some prime. If not, let me see. So I could either write it as 120 into 2, right? Or 60 into 4, whichever way you want to do. But let's factorize it more. So 120 into 2, what is 120 to factorize it? I could write it as 15 into 4. I'm sorry, it is going to be 60 into 2, right? So already there is a 2. So how could I factorize 60? I could write it as 15 into 4 into 2 into 2. But let me try to express this in terms of primes. Okay. So what is 15? Again, you factorize 3 into 5. 4 is 2 into 2. And you have another 2. Okay. So now I've got like this. So what will I do now is to see if I can express this in terms of exponents, right? So 3 power 1 into 5 power 1 into 2 power 4. Can I write like this?
Yes, sir.
Yeah. So then how will you do now? I have to calculate phi of this.
It's using 4 and 2, sir.
Exactly. So you now have to, I'm sorry. Okay. You now have to use the property where you will use the fourth property now and the third property and then go on to find what is phi of 3 into phi of 5 into phi of 2 power 4. So these two, I think you can directly use the second property. So it's going to be number of elements is going to be 2 into 4. 2 power 4
minus 2 power 3.
so 2 power 4 you have to use this. So it's going to be 2 power 4 minus 2 power 3. P to the power of E. 2 is prime, right? 2 power 4 minus 2 power 3. So what is this value? 16 minus 8. What does that come?
8 and total answer is 64.
Okay, so the answer comes to, so 32 into 2. So their answer comes to 64, which means there are 64 elements in that set, phi of 240, such a way that they are lesser than and relatively prime to this. How many are able to understand this? I was quite fast, but I hope, can you raise your hands if you have understood, you're able to apply these Euler's formula, right? You need some practice. We are only dealing with small numbers. I'm not going to go beyond, 3-digit and all that. It will become complex because you have to factorize this. Please understand, the larger the value of n that becomes, factorizing that number becomes difficult. But the other way around is easy. Given these product of these numbers, you can compute the function and get the value of n. But the reverse of that will become difficult. This is how RSA tries to play, right? Right, in terms of this. So I'm going to give you two more problems. You have to tell me. So it has to be carefully dealt because there are some rules, right? I'm saying these should be relatively prime and all this. What is phi of 49? Anyone?
7 square minus 7.
Okay, good. So I'm not sure if you looked at the solution there. How will you generally try to do this? I will instead look at this. I can express this as 7 into 7. Then I will go and directly use the third property. Can I do that?
Take 7 squares.
You can't do this because these two are not relatively prime, right? So that is the point here. The GCD will be 7, correct? And so, so that being said, you have to use such a way that 49 could be expressed as 7 square and 7 is a prime, and then you could use 7 square minus 7 power 1. What is the value that comes? 49 minus 7.
42.
Huh?
42.
42, yeah. So that is the value that comes for this case, right? So the number of elements in that set that are going to be relatively prime to that is going to be 42. I hope you're able to understand. So last example. Okay, so can you tell me Z14 star? What is the answer of Z14 star? You have to differentiate what is Euler's torsion function and what is Z set that we're talking. What is Z14 star? So if I give like this, I want you to tell me the number of elements in the set, correct? Such a way that is the elements are smaller and prime to this. So
Is
1
it 1 to 13?
1 to 13. Now you have to look at whether 14 is a prime number or not, right? So if I bring in 2 here, GCD of 2 and 14 is not 1, right? 2 can divide that, right? 14. So that is going to be the greatest common divisor. So that will not come.
1, 3, 5, 9, 11 and 13.
Okay, so how many elements are there here?
It's totally 6. I mean,
You have 6 elements. Can you now use Euler's function and go on to prove it?
Yes, sir. It's 7 into 2 and
7 into
6 into
Very
1.
good. So that will become phi of 7 into phi of 2, which will be what? 6 into 1, right? So you have the answer as 6. I hope you understood this. So why are we doing that is because we're going to choose one of this element in the set as the public key and find out the inverse of that such a way that is also going to be part of the set. So that's the beauty that you're going to deal with, right? So you should understand Euler's torsion function so that we can do this. There is one interesting point. Suppose if the value of n is greater than 2, right? The value of phi of n will always be even. So if you look at here, phi of n you computed is actually 6. So all these values that you're looking at is all even numbers, right? So that is the beauty. So think that also, so that you can also cross check whether you're doing it correctly. Okay, so having taught you Euler's torsion function, let us now go to the RSA algorithm. So how RSA algorithm is being done is it uses a concept called trapdoor one-way function. So that is the beauty here, right? So ideally what we are trying to do here is, this is just to explain you a function. Say suppose you have given x, you are applying a function over x to compute y. This is a function, right? You are applying a function. Now, what do you mean by one-way function is given x, it is going to be easy to compute y using this function. But given y, right, you want to find out what is x, you need to find out f inverse of y. But computing the inverse function is going to be difficult. That is what is called as one-way function. One-way function means that it's going to satisfy two properties. The function f is going to be easy to compute. So given x, y equal to f of x can be easily computed. But the inverse of this, you want to get x out of y, it's going to be computationally infeasible, at least in polynomial time, to basically compute it. So that is the point of one-way function. But then what RSA tries to do is it goes on to use a third property. So this is called trapdoor one-way function. See, if you are given y and you're given another secret that is called the trapdoor, then you can easily compute x. So that trapdoor secret is your private key, which no one knows. Okay, so let's try to apply how this trapdoor one-way function comes in. So this is a summary, which basically means one-way function f is easy to compute, but f inverse is going to be difficult to compute. The trapdoor says the third property. Now, given the y, right, and a trapdoor, x can be computed easily. So let's now apply this in what RSA tries to do, and I'm going to give you that example. So how are we going to do here is this. So we are going to take two prime numbers, P and Q. Ideally for RSA, they choose such a way that these are two large prime numbers. So what is Bob going to do? Bob is going to choose two large prime numbers and apply a function over these prime numbers. So what is that function he's going to do is he's just going to multiply these two prime numbers, right? And he will get a value n. That value n is the modulus value. Okay. So now he is going to get a very large value of n, right? But since he knows the prime numbers and he has multiplied these two prime numbers using the function as multiplication, he is able to get the value of n. Okay, this is going to be a one-way function because if you do not know these primes, right, it will be very difficult to factorize n, right, doing the inverse of this. So given n, if you have to find p and q, that's going to be difficult. That is the factorization problem where it becomes a one-way function. So what is the trapdoor secret here, right? Is this where we are going to apply this logic. So I hope you got the point here. So the RSA, the key generation part, whether Bob is going to generate keys or Alice is going to generate his pair of keys, they have to choose two large prime numbers, multiply those two large prime numbers to basically get the value of n. But factorizing n as a large value of n is going to be difficult. The inverse of that is going to be difficult. So it becomes a one-way function. So unless or until you do not have another function. So f inverse is going to be difficult, right? But f is going to be easy, correct? Say you have another function g, which is having the trapdoor secret, which is what Bob is going to do, right? Then it's going to be easier to do. So let's try to apply that for the RSA part. So I want you to carefully focus now and look at this picture. This is going to be the entire algorithm, which is going to deal with prime numbers, which is going to deal with Euler's torsion function, which is going to deal with fast exponentiation, so much things very nicely covered. So I want you to appreciate this and then learn so that you don't find it difficult. So let's now look at this. Okay. So the point now is I'm going to assume here Alice wants to send message to Bob. Okay. So what he has to do is Bob has to generate the key. So key generation algorithm is the first step. That is what I'm going to teach you now. So the key generation algorithm is going to be such a way, right? He is going to do this. He is going to select two large prime numbers P and Q, right? And then he's going to multiply that to get the value of n. So whenever I say n is going to be the modulus value, right? So from this n, he is going to find out phi of n, which is the Euler's torsion function. Okay, so the key calculation is going to be based on the value n. Phi of n is going to be easier because you know P and Q. So Bob can easily find out what is P. So let me show you the algorithm. So I want you to look at the algorithm. So this is the RSA key generation algorithm part. Okay, so look at the first line here. So Bob is going to select two large primes P and Q. Such a way these are not P is not equal to Q. So that is the first step. And then you have to multiply these two prime numbers to get the modulus value, the n value. But you're not going to stop there. This is where the algorithm starts for generating a key. So you, given the n, you have to find out phi of n. You know that it is a product of these two primes. So you simply apply, the rule 2 and rule 3, right? So what will be the value? It will be p minus 1 into q minus 1. Okay, so now you have found out phi of n. So from phi of n, you are going to, so what ideally you're going to do now is you have to choose your public and private key pairs, right? This is what is going to be there. So I'm going to use, letter say E to represent the public key and letter D to represent the private key, right? So let's look at this now. So I'm going to select, the public key E such a way that E is going to be a value greater than 1 and lesser than phi of n, right? So what does it mean here? You're going to choose one of the elements in the set, right? Such a way that E is going to be co-prime to phi of n. So this is a very important point, right? So we'll understand this with an example, but just try to take up the point here. So having computed phi of n, right? So say you get some value as 13, right? So now I need to choose, I need to select. So what are we trying to do here? We are trying to do set 13 star. That is the point here, and choose one of the elements such, in that set, such a way that E is going to be that element that you're choosing, which is going to be smaller than 13, which is obviously going to be greater than 1. That is 1 point because it's a key value, right? And it should be lesser than 13 and it should be relatively prime to phi of n. So once you have selected E, which becomes your public key, you need to find the inverse of this public key, which will be your private key. So how are you going to find the inverse of that is we are going to find the private key D, which is going to be E inverse mod phi of n. Okay. So what does it mean is E and D are going to be the inverse of each other, the multiplicative inverse of each other. Why do I say multiplicative inverse of each other is if you multiply E and D and do a mod with phi of n, right? The remainder will be 1. So the GCD of E and D, right? If you go on to take, that's going to be 1. So these are going to be relatively prime numbers. So how will you find D, right? It's going to be, you have to find the inverse of E, right? Mod phi of n. So find out the inverse of E, mod phi of n. We are going to use extended GCD algorithm. Okay. So the goal is, now that is the end of the game. So you found out E and D, you have found out the pairs. Then what you do is you are going to announce to the, the public, your public key, right? So how are you going to announce your public key is basically you're not just sending E, you're also sending n. Okay. So this is going to be the public key. Okay. The private key is something you have to keep it secret. The D value is going to be your trapdoor, your secret. Okay. Please do not share P, Q and phi of n. Then your entire algorithm fails. Right. So what are you sharing to your public is your private key, public key, which is going to be the exponent E value. This is the E value and the n value. The modulus value is going to be used because we're going to do modular exponentiation. So this is going to be a public key, right? And your private key is going to be D, right? That is what Bob keeps as his personal secrecy, the trapdoor. and the E and N is going to be shared. Right. So I hope you're able to get the key generation algorithm, but if you apply these rules, you'll be able to understand this. Okay. So once the public key is being distributed, what are we going to do? I will show you here. So I hope now you look at this picture, it gives you a much better idea. Okay. So we have selected E and D based on phi of N. Okay. We have hidden phi of N, we have hidden P and Q. We are not sharing all that. Obviously, we are not sharing the D. What we are sharing is only E and D to the public. Now, when Alice wants to send the message to Bob, he has to use the public key, which is E of N. So why is it like E of N? Is because we are using modular exponentiation to do encryption. So what is modular exponentiation is very simple here. So it goes like this. Ultimately, you are going to do mod of N, right? You have your plain text. So what you do is you take and compute P to the power of E. That is the exponent. So the public key is treated as an exponent. P to the power of E mod N value. That is what is going to be your cipher text. This is what Alice is going to do. Okay. So the cipher text that he is going to transmit to Bob, right? Bob is not going to do, E root C to get that. That's going to be very difficult to do. Instead, this is a one-way function. And in order to find out the inverse of that, which means you need to know the secret, and that secret is D. Okay, so what you're going to do is, given the cipher, you're going to you do C to the power of D. D is your private key. So Bob will use this and get back the plain text. So that is the beauty of the RSA algorithm, where a one-way function is being used. We are using modular exponentiation. Why is it called modular exponentiation? You're doing modular arithmetic only, but you're dealing with exponents. So the public key is an exponent value. The private key is an exponent value. And how did you get an E and D from this? Is from your key generation algorithm. That is based on the Euler distortion function. And from that set, you have chosen E. And the other element is going to be an element in that set, which is going to be inverse of relatively prime. E and D are going to be co-prime to each other. So for that, I need to use the extended algorithm. How many are able to understand some part of what I was trying to convey in the, frankly tell me, how many are able to understand as such the algorithm of what Alice is trying to do, what Bob is trying to do? Is anyone able to understand that? Can you raise your hands? Okay, so no one has understood. Okay, Bhuvan has understood.
Partially, sir.
Partly. So which part you're not able to understand? So we have to do this. We have to actually compute, this modular exponentiation. What is this value, right? So if I give you an example and then tell you, then you will be able to understand this practically. So the point here is what Alias is doing at the encryption side is going to do modular exponentiation. So what he has the plain text. This plain text I need to convert to integer, right? Say you have A, B, C, D, right? Like that. I have to choose the corresponding number of A, right? So you map A to 0, B to 1, C to 2. So you have 25 letters, right? And so you go on to map that and then use these integers to go on to apply that. So anyway, let's see that in the problem. So you have the plain text and you have the tuple. This is called the tuple, the pair, the public key. So E and N. So he is going to use the fast exponentiation algorithm. Instead of traditionally doing multiplication, P multiplied E times, right? And then finding out the value, take mod N and get the remainder out of that. That will be your cipher. We're going to use the square and multiply method, right? And what is decryption side? You got the cipher, you got the D and N, right? You're going to do C to the power of D mod N using fast exponentiation algorithm. So this is the encryption and decryption aspect of algorithm. And the key generation algorithm. So these are the three algorithms that comes in. So here we have already seen Euler distortion function, but I have to now tell you how you have to find the inverse. Teach you how to do fast exponentiation. Fast exponentiation is slightly simple, so we will try to do that. But in real time, if you look at the P and key values are going to be some around 115. So long, right? You choose that and then you take the product of that and then you get your value of N. Without knowing what is that two primes that you have multiplied, you've got n. Factorizing n to get p and q is going to be very difficult. That is what is one-way function. That is why we are finding all this e and d, right? So that you can get the trapdoor secret. I hope you're able to understand. So this is how the algorithm goes. Now, if e comes and tries to hack this, he does not know the trapdoor secret. What he will try to do is he will try to find f inverse. What is f inverse? You have to get p from your cipher. So he will try to use the eth root of c, right? Since e is known, to compute that, which will be very difficult to do, which will be of exponential complexity. But fast exponentiation algorithms tries to quickly do it in polynomial time, right? And you could try to handle this. So that is the point in terms of hacking it, but don't worry about breaking ciphers. We are not going to deal with breaking ciphers. But yes, RSA is designed to do that. So I will now end the class, right, by just giving you an example. And then we will use on Monday's class of how fast exponentiation all this works. So let me do this. I want you can do a part of it. It becomes easy to do. You will understand what is the algorithm trying to do. So let's now do this. Bob is going to generate public and private keys. So what he has done is he has chosen two prime numbers p and q. You can write down this. I'm going to ask a question before we wind here. So he's choosing two prime numbers 7 and 11. P and q value is 7 and 11. They are not same. So what will be the first step that Bob has to do? Can you tell me? Having chosen the prime numbers P and Q, what should Bob do? Can anyone tell me?
N.
N equal to P and Q.
So what he has to do now? So he is going to now multiply these two prime numbers. So what will be the value of N? Can anyone tell me? What will be the value of N?
77.
77. Very good. So it's going to be what? 7 into 11, 11. So that's going to be 77, right? So now what's the next step? You have to find the Euler's torsion function. So Bob is going to find Euler's torsion. Can you tell me what is phi of N value? So N is basically 7 into 11.
So 60.
So how did you do that? Since you already had P and Q, it was very easy for you to basically do phi of P, right? So this becomes 6 into 10. That is phi of 77. So the value comes to 60. So you have done till this now. Next comes your step where you have to choose a value which is going to be your E value, right? Such a way that the E value is going to be greater than 1 and is going to be less than 60. Okay. Also, it's part of that set, right? It is part of set 60 star. This is what we are trying to do here. 60 is what? Z phi of N star. So I need to choose E among this set. Such a way that it is co-prime, it is part of this set, right? And a value greater than 1 because I don't want the key to be 1, right? So choose exponent such a way that it is lesser than 60 and it is relatively prime to phi of N. So can you tell me what will be Z60 star? Some of the elements in Z60 star, can you tell me? 1 will come. Anything else?
7.
7 will come. Very good. Then?
And 11.
8 will not come. 9 will not come.
11,
10 will not come. 11 will come. Then?
13.
13 will come. So it will go on. So here you have the choice now to choose one of the element in the set. So the example that is given in Ferozon has chosen 13. It is not mandatory that you have to choose 13. You can choose even 7, right? But don't choose 1. You can also choose something which is hard. So you have to choose one of the elements in that set and that becomes your E. So E value now is say 13. Using 13 now, I have to find out D. So what is going to be D? D is going to be 13 inverse mod. What you have to calculate? 13 inverse mod. Please be very careful. Don't put 77 here. It's going to be 13 inverse mod 60. So you have to calculate what is 13 inverse mod 60.
73.
So you already done that. Okay. So here I will teach you an extended Euclidean. I'm not going to do this because of the lack of time. 13 inverse mod 60. So the idea here is if I have to find such a way that E and D are co-prime to each other, I should ensure that E into D mod 60 should be equal to 1. So GCD of E and D is going to be 1. So this is such a way that D is E inverse mod 60. Right. So this is what you have to do. For that to get the inverse pair, multiplicative inverse pair, I have algorithm. So this is on the Bob's side that he computes the private key, and then what he will share to the public. Can anyone tell me what he will share to the public? Be very careful what you're sharing to the public. You have to share e comma n. This is key. So what Bob is trying to share to the public, he will share 13 comma what 77. Don't share phi of n value, or don't share p and q. These all should be hidden. This is what will be shared to the public. Okay. So you know that 77 I can factorize, sir. 77 I can factorize as 7 into 11. It is easy. But please think n is a very large value in real, right? So it becomes difficult to factorize. Anyway, so now I'll quickly show you so that you can understand this. So what we are going to do now. So ultimately now he has shared this. Here the d value is 37. I'll teach you how you got d 37 value in the next class. But now what he is doing is Alice wants to send a plain text value 5 to Bob. So we'll deal with very small example. So plain text 5 to Bob. So which means what? Value is 5, right? He has got the e of n, which is basically what? 13 comma 77. So what he has to do, Alice has to compute p power e mod n. So what is p power e mod n? 5 power 13 mod 77 is what he has to calculate. You will know the difficulty that multiplying 5 13 times and then I'm trying to divide by 77 to get the remainder is going to take you time. So I will teach you fast exponentiation where you will treat this exponent as bits and then do a square and multiply method to easily compute this. You can also calculator, but you need to if you use fast exponentiation, you will be able to correctly get the remainder part. Okay, so once you transfer the ciphertext to Bob, Bob has to do what? C to the power of d mod n is what? So he's got 26. So 26 to the power of d. What is d? 37 is what is found out. 26 to the power of the mod n, which is 77. You have to find out. If you get back 5, the answer is correct. Okay, that is what this entire algorithm. So I need to teach you now fast exponentiation as well as to find the d, the multiplicator inverse, so that you can use this for problems. How many are able to understand RSA? Some positive voices, those who have understood RSA algorithm, right? The only key now is to understand how fast exponentiation works and how multiplicative inverse. Okay, 3 of you have understood. Can I take it like that? Partly, how many have understood? Okay, partly. Okay. So now whatever logic that I've told you so far, right? Till that, I'm not telling you, perform fast exponentiation now because I not taught you, right? I'm also to find the inverse of that. Given finding out E, you've chosen E. So choosing E is in your hand, but you need to find out Euler's distortion function, right? You can choose anyone on that set as E. Now D is going to be such a way that it's going to belong to that set. So you saw that 37 was found out. So 13 and 37 are belonging to that set Z60 star. Such a way, if you multiply 13 into 37 and do mod 60, it will be 1 because E and D are co-prime to each other. So this inverse pair that you're finding out gives you the pair public and private key pair. That is the beauty of RSA. Anyway, Monday morning, I will complete this and you will work out a problem. With that, we will wind off the module 7 discussion. Module 5, I've shared you, 3 videos, in fact, right, on GSM comprehensively we have covered. UMTS 3G architectural, and I will give you a short video on Saturday. Okay, so with that, our syllabus I've justified to some aspect on module 5. And module 7, we are limiting to only data security, though we could get onto GSM and understand the security aspect, Wi-Fi and understand the security. You will understand that it's basically symmetry key, RSA and all that being used there. So that's the thing that I wanted to restrict only to data security. And with that, Tuesday class, we will have a short quiz and I will recap from the fact point of view of how we can take it forward. Is that fine, guys? I hope you're comfortable with the plan. So Saturday, we will sit as you told for the J demo. I hope you will finish all your lab fats, right? And we will sit from 11:30 to 1:30. Is that time fine for all of you? Saturday?
Yes, sir.
Okay,
Yes,
yeah.
sir.
Yeah, so I'll finish with that. So thank you. So let's meet on Saturday then. Bye bye then. Yeah.
Thank you,
Bye
sir.
guys. Yeah.